Welcome everyone! In this video, we will continue introducing counter modes, but with a slightly different application from the previous ones.
Yes, it won't be as cliched as the ones before, so here's what we are going to talk about.
We will talk about incremental encoders, also known as rotary encoders.
An incremental encoder, also known as a rotary encoder, signals a given amount of angular rotation with a fixed number of pulses, which can be counted to determine the relative position of your rotary axis. Such sensors can be found, for example, in computer-controlled production lines and workstations. In these devices and in electric motors in general, rotational characteristics are often measured using devices based on this technology. The microcontrollers often support the processing of signals from such sensors, so it's worthwhile to learn about this function in counting and timing modules. In the introduction to the input capture mode, we learned how the timer counter modules can be used to detect events occurring outside the microcontroller. To process the signals from an encoder, a very similar task is performed.
Rotary encoders can be, without being exhaustive, magnetic, mechanical, or optical.
As an example, let's look at an optical incremental encoder illustrated in the screen. Imagine that the disk in the diagram is rotating clockwise at a constant angular speed. A, B, and Z are phototransistors that detect the light emitted by the light source on the other side of the disk. There are 8 evenly spaced windows on the disk through which A and B can detect light from their counterparts. Z can detect light through only one window, the 0 point of the disk. As the dial rotates, the outputs of A, B, and Z are shown. When they detect light, their output is a logic high signal, otherwise their output is a logic low signal. We can observe the phase shift between outputs A and B, which helps to determine the direction of rotation. Imagine, if the dial were spinning in the opposite direction, output B would switch to high a little earlier than output A.
You can mount the dial shown in the figure on one end of a rotating shaft and monitor the rotation on your shaft. Later in chapter 17, we will learn how to control motors. For this example, we will use this DC motor, which also contains an encoder unit, here at the end of the shaft.
In that chapter, you will also need to know how to configure it, so let's take a look at what settings you can work with, as we did in previous modes. First of all, in encoder interface mode, we need to set which input we are working with. In general, you can use only A, only B, or both A and B. Of course, these signals must be tied to the appropriate legs of our counter and timer module. You can set the 2-input mode for TIM1, for example, by selecting encoder mode in the Combined Channels field. In the parameter settings, the encoder mode is set to encoder mode TI1 and TI2. If you want to use the 0 position signal 2, you can connect it to a generic GPIO leg and set it to external interrupt as recommended by the manufacturer of the microcontroller. Then, the inputs must be configured and input filtering can be applied where appropriate. For the sake of the example, we have set up detection on both inputs for a folding edge, and we specify 6 samples for input filtering.
In the next step, we must choose on which input we want to count the pulses of the encoder. In some cases, we can do this for the rising, falling, or both edges of several inputs. With the current settings, we count on the falling edge of both inputs. If you only want to count on the basis of one of them, select encoder mode TI1 or encoder mode TI2.
Finally, we also need to set the count limit in the dedicated register. The counting register counts up or down between 0 and the limit, according to the direction of rotation. For the sake of example, let's use an encoder that gives one pulse every 1 degree of angular rotation, so we set this value to 360.
There is nothing left to do but start the counter and timer module.
The counter register will always contain the value corresponding to the current position. Information about the direction of rotation is usually found in one of the registers of the counter and timer modules, which the microcontroller updates itself based on the inputs. If a sensor signal indicating the reference point is used, the counter register value can be changed at the same point during each rotation.
It is important to note that the encoder interface only provides information about the current position, in this case the angular position of our axis. To determine other dynamic characteristics, for example angular velocity or angular acceleration, we have to resort to other solutions.
The angular velocity can be determined by calling an external interrupt routine at the reference point of the encoder, starting another counter module, and measuring the time until the next reference point is reached.
In the introduction of the first video, Watchdog Timer was mentioned as a standalone peripheral that protects against failures and interruptions caused by possible software errors, thus facilitating the real-time operation of our system. It's named as such because while the dog protects its owner from intruders, the timer protects the software from errors and freezes.
Generally speaking, Watchdog is a continuous down-counting timer that generates a reboot when it reaches 0, meaning its timer has expired. To avoid this, we need to reset the counter to a higher value at appropriate intervals. This way, if our software stops running, we can assume that the Watchdog timer will not be reset. However, the expired timer will cause our software to restart, thus freeing our system from the stall caused by the failure.
It is legitimate to ask what happens if we are unfortunate enough to be stuck in an infinite loop in our software, in a way that the Watchdog reset happens regularly.
The microcontroller manufacturers have been clever enough to think about this, so the generic Watchdog module is usually either supplemented with a window function, the functionality of which will be discussed later, or made available as a completely independent peripheral.
Watchdog peripherals usually have few configuration options due to their simple operating mechanism. Let's take a look at them.
For security reasons, it is standard practice for microcontroller manufacturers to only modify certain registers of the Watchdog module after entering the correct password, otherwise the settings will not take effect. This password must be entered in a dedicated register. Similar to the traditional counter and timer modules, Watchdog allows you to set different presets and thus change the length of the timer.
Watchdog modules also have a register where you can set a count limit. Of course, we are also limited by the resolution of the counter. A common way to wind up the Watchdog is to enter the password for the reload in the password register mentioned above. This will cause the value of the count limit register to be copied into the count register, thus replenishing the value of the count register that has been reduced in the meantime.
In some cases, Watchdog can be supplemented with a so-called window, which serves the purpose of generating a restart when the timer expires and when the Watchdog is recharged too often. In the case of a Watchdog module with a window, we still need to set the window limit, which allows us to define at least how long we should wait between two counter resets. We'll quickly show you what this means. Between the maximum value of the counter and the limit we have set is the so-called forbidden range. If you attempt to redraw a counter in the forbidden range, the peripheral will immediately generate a restart. The operation of a traditional Watchdog differs in that you can reset the counter at any time, and the restart will only occur if you fail to do so and the counter reaches 0.
Great! Now that we understand the Watchdog, let's move on to another special timer.
In our embedded systems for complex tasks, we often use some kind of embedded operating system to schedule tasks. However, real-time operation of the operating system cannot be ensured without accurate timing. In most cases, the operating system running on microcontrollers uses a dedicated counter and timer module, the SysTick Timer to perform scheduling tasks. This timer is found in almost all Cortex-M based microcontrollers, which are developed specifically for embedded systems. The SysTick is a 24-bit resolution down-counting module that is set by embedded operating systems during the initialization phase. Its timing can be changed in the operating system configuration parameters and at the expiration of which the operating system scheduler runs and decides which tasks to run.
This timer will be important in chapters 21 and 22 of the curriculum, since these chapters are about operating systems running on microcontrollers. We've completed the theoretical part of chapter 15, but if I were you, I'd watch the following video, as we'll apply what we've learned and we'll create 2 timer programs. Until then, we'll say goodbye.
Bye!